Hi all, let's go over what your first test will be like. What I've done here as I created this, beside each of the problem numbers, I've referenced where I got it from the MyLab assignment. So beside each of the numbers, if you want more practice problems, all you have to do is go into the MyLab assignments and look at the problems referenced, and you can get as many different iterations of these as you'd like. For this first problem, the key on it is making sure that you understand anytime that there's algebra to be done, it must be done before the calculus. So in this problem, I have to go ahead and FOIL out that 9x plus 1 times 4 minus x. Went ahead and FOILed that out, and 9x times 4 gave me the 36x. Then I had minus 9x squared plus 4 and minus x. The only thing I've done from this step to this step is I wrote it in descending order, and I combined the 36x minus x to give me 35x over here. And then after that, this is where we do our integration. So we've done the algebra first here. That's all I can do with the algebra. From there, I said, let's integrate negative 9x to the second. That became negative 9x to the third divided by 3 for my answer, negative 3x cubed. This 35x becomes 35x to the second divided by 2. That's where that term comes from. Then, of course, 4 is understood to be 4x to the 0, so it becomes 4x to the first. And don't forget your plus your constant of integration. Cool stuff. If I look at the next one here, I have the integral of 9 over x to the fifth plus 3 minus 9x squared. Again, you have to simplify that algebraically before you're ready to use your power rule in the integration. 9 over x to the fifth has to be written as 9x to the negative fifth power. 3 doesn't need to be rewritten. But then the last term, minus 9 over x to the second, becomes minus 9x to the negative 2. When you have the negative exponents in for your terms of x, then you can use your power rule. So that first term, remember, we're adding 1 to the exponent. Negative 9x to the fifth becomes negative 9x to the negative fourth. Divided by negative 4, I wrote that as negative 9 over 4 x to the negative fourth. The 3 becomes 3x, and then the negative 9x to the negative 2 becomes negative 9x to the negative 1 divided by negative 1, which is why that negative became a positive since I had to divide by the negative 1 in that step, plus our constant of integration. I would not want the answer in this format just because it's ugly with the negative exponents. I want to write it back in the form of the original question. So I can say, okay, negative 9 over 4x to the negative 4 is better written as negative 9 over 4x to the fourth. 3x, no way to rewrite it. Plus 9x to the negative 1 becomes plus 9 over x. And then we have plus our constant of integration. For the third problem, you'll notice these first three problems, they're all pretty similar. We're going to have to do some algebra first, and then go ahead and use our principles of the power rule for integration. So in number 3 here, I gave you the polynomial 6x to the ninth plus 4x to the fifth divided by x to the fourth. So this is a rational function since it's a polynomial over a polynomial. And then I can say, well, okay, I know I need to distribute that x to the fourth in the denominator into both terms in the numerator. When I do that, I get 6x to the fifth plus 4x to the first. Ready to use our power rule. 6x to the fifth becomes 6x to the sixth divided by 6. That's why the 6 is gone. And then I would have 4x to the second over 2. 4 over 2 gives me the 2 coefficient there. Please always remember to put your constant of integration in each of these. I would certainly count off if you forget your plus c. For the next problem here, we have the minor application from this first section. This is similar to number 99 from the 4.9 book homework. It says, given the following acceleration function of an object along a line, find the position function with a given initial velocity and position. So we know our acceleration is 0.6 times whatever the time is. The velocity at time 0 is 0. The position at time 0 is 5. And we're not given any units or anything, so we don't have to worry about units for our answer. We know that velocity is the integral of the acceleration function. So that's exactly what I did. And I would expect to see the dt in there. So it's the integral of 0.6t with respect to t. When we integrate that, I'll get 0.6t to the second over 2. That's where I'm getting the 0.3t to the second plus the constant of integration. Now, at that point, I need to solve out for that plus c. So I can say that's where I'm using my initial conditions here. The velocity at time 0 is 0. But if you plug a 0 into your velocity function, you'll get 0.3 times 0 squared plus c is 0. That's just going to give us that this value of c is 0. And always in these problems, c is just your original velocity anyway. So we knew that c would be 0 in this case, and then that our velocity function would just be that 0.3 t to the second. So now the position is the integral of the velocity function with respect to time. When I do that, 0.3t squared becomes 0.3t to the third over 3, which is why the coefficient changed to 0.1 there, plus our constant of integration. Now, I could have just went ahead and said the constant of integration is 5 because s sub 0 is 5, but I wanted to prepare you in the event that I gave you something else other than s sub 0. If I did s sub 1 or s sub 2 or s sub 3, you would have to plug that into the problem. So I went ahead and did that with 0. S of 0 gives me 0.1 times 0 to the third plus the constant of integration is 5. But because s of 0 cancels out the variable terms, you're just left with c equals 0.5 here. Sorry, 5, not 0.5. C equals 5 here. And then that goes into our answer. So we can say the position function is 0.1 t to the third plus 5. Nice problem. Now, that's all of the 4.9 problems on the test. The next section, you'll notice I put the problems in the order that the homework went. The next problem is from section 5.1. And the main point of this section was to get you to do left, right, and midpoint Riemann sum estimations for area under a curve. And so for this problem, we were looking at f of x is equal to the parabola 2x squared from 1 to 6. We're wanting the left, right, and midpoint Riemann sum estimate for the area under the curve with 5 subdivisions. So the first thing to do in any problem like this is to think about the width of each of your rectangle approximations for the curve. Well, each one is going to have a width from, you always say it's the interval. So in general, delta x is b minus a over n. So we'd say, well, in this case, it's 6 minus 1 over 5. Works out nicely, 5 over 5. The width of each rectangle is going to be 1. So the left-hand rectangle estimate is going to be that common width of 1 times the summation of the heights. And you say, well, okay. The first height that you're going to do is on the rectangle that starts at 1 and ends at 2. Its height is going to be f of 1. Then you're going to, for each of the successive rectangles heights through here, you're just going to add that delta x to the value that you're inputting into your function. So since delta x is 1, as soon as I know that my first height is f of 1, second height has to be f of 2, third height f of 3, f of 4, f of 5. We know that's the fifth and final rectangle. It's going to go from 5 to 6. I don't need f of 6 here since it's a left-hand rectangle approximation. So we have our common width times the summation of the 5 heights. You're going to plug those 5 heights into your function. So this first value here, that's when you plug a 1 in. 2 times 1 squared is 2. 2 times 2 squared is 8. 2 times 3 squared, that's 2 times 9 is 18. 2 times 4 squared, that's 2 times 16 is 32. And then lastly, the 50, it would come from f of 5. You'd say, well, that's just 2 times 5 squared. 2 times 25 is 50. We multiply this sum by 1. Obviously, multiplying by 1 doesn't change anything. And we get that the left-hand rectangle approximation using L5 is 110. Now, we know that this underestimates the true area under the curve for any increasing function. So I can say, well, the lower bound of what the integral from 1 to 6 is would be 110. Now, if I wanted to find the upper bound, that would be R5. And the way I think about R5, again, you say it's the common width 1 times the summation of the heights. Well, notice it can't have that very first height because that's the left-hand side of the first rectangle. Its height is going to start with the right-hand side of the first rectangle, which is f of 2. So you'll notice it's all of these heights, f of 2 through f of 5, and then plus the right-hand side of your very last rectangle, which would end at x equals 6, so it's the function at 6. So you can say, well, R5 is the exact same thing as L5, with the exception that it's taking all the heights minus the first one, and then add in the last one, f of 6. So then at that point, just like I did with L of 5, I plug those heights into the function. F of 2 is 2 times 2 squared. F of 3, 2 times 3 squared. F of 4, 2 times 4 squared. F of 5, 2 times 5 squared. And F of 6, you'd have your 2 times 36 is 72. So then I just did this in my head when I found it out because I was just thinking, well, okay, it's the same thing as what I had up here, minus 2 plus 72. So it's 70 more than the left-hand approximation, which is why it came out to be 180 there. Now, for the midpoint approximation, instead of using the left hand that starts at 1 or the right hand that starts at 2, your very first rectangle's height is going to start at the midpoint of your first rectangle. Well, since we know delta x is 1, we know that the first rectangle starts at 1 and goes to 2. The midpoint of that rectangle starting at 1 and going to 2 is going to be at 1.5. So I can say, well, I need my common width 1 times my first height there. Well, my first height is going to have to be f of 1.5. Once you get that first height, everything is easy after that because we know each height has to be taken at a delta x difference successively each one. So once I get that f of 1.5, the midpoint of the first rectangle, I know the next one's going to be f of 2.5, f of 3.5, f of 4.5, and f of 5.5. The height of your last rectangle needs to be determined by its midpoint. It's going from 5 to 6. Its midpoint is going to be at f of 5.5. We plug each of these functional values in. For example, in the first one, 1.5 squared is 2.25. We multiply that by 2, I get 4.5. 2.25 squared is 6.25 times 2 is 12.5. 3.5 squared is 12.25 times 5 is 24.5. 4.5 squared is 20.25 times 2 gives me my 40.5. And then lastly, 5.5 squared is 30.25 times 2 gives me my 60.5. We take the summation of these, in this case just times 1, to get our 142.5, which we know is the more accurate representation of the area under the curve. The weakness of this, though, is we don't know if it overestimates or underestimates, where we know this is our lower bound here. We know this is our upper bound. And the only thing we can say about this is that it is more accurate, but lower or upper, we don't know. But now you don't need to put any of that for the test. Just what I have here is all you would need. For question 6, it's just some operations with the sigma notation, summation notation. If I say I want the summation from m equals 1 to 3 of 3m plus 3 over 5, you need to know all this means is that you're going to be evaluating this function on the inside of this summation, starting at 1, then at 2, then at 3, and adding those 3 terms. So the function evaluated at 1 is 3 times 1 plus 3, that's 6 over 5. Then I say plus. The function evaluated at 2, you'd say, well, 3 times 2 plus 9. That would give me 6 plus 3, 9 over 5 for my second term. Keep on adding your third term. Well, it's when m is 3. 3 times 3 is 9, plus 3 is 12, divided by 5. We'll get our 3 terms right there. The summation of those, I get my 27 over 5. For part B, slightly trickier. You need to understand that there are actually 6 terms here because you're going to have the j equals 0 term and then j equals 1, 2, 3, 4, 5. So I can say, well, all right, we're supposed to sum up when j is all of those values for the function 4j minus 7 on the inside. When j is 0, well, when j is 0, my inside is just going to be 4 times 0 minus 7. I get the negative 7. Plus, when j is 1. So this is my 0 term, this is my 1 term, 2 term, 3rd term, 4th term, and when j is 5 term. We plug those in now. We can say, well, for the first term here, 4 times 1 is 4, minus 7 is a negative 3. I wanted to show it's a summation of the solutions, so I put negative 7 plus negative 3 plus, when j is 2, you'd get 8 minus 7 for 1, plus, when j is 3, you'd get 12 minus 7 is 5, plus, when j is 4, you'd get 16 minus 7, which comes out to be 9, plus, when j is 5, you'd get 20 minus 7 for 13 there. Add all of those together, you get your 18. Up next, I'm wanting you to be able, notice I say here, do not integrate or use Riemann sums to evaluate this. I want you to use geometry on this problem, just like the homework wanted you to do. Now, in the homework, I couldn't force you to do it geometrically because my lab wouldn't know for sure you're not using some other technique. But on a test, I'll expect to see something like this to show me that you're that's why I say sketch a graph of the integral and then shade the regions that lead towards your solution. Now, I ended up not shading here just because I didn't want to make a mess, but I've labeled my areas. So it'd be this area plus this area plus this area here. Whenever we say the integral from negative 5 to 7 of the absolute value of x minus 3 with respect to x, please remember the absolute value function is just a v function starting at the origin. This is that function shifted down 3 units. I just said, well, okay, it's the shape of a v shifted down 3 units, so that means we know it's going to have an x-intercept at positive 3 and an x-intercept over here at negative 3. And then I can say, okay, we know it's going to begin when x is negative 5. When x is negative 5, I'd get the absolute value of negative 5 is 5, minus 3 is 2. That's where I got the ordered pair negative 5, 2 up there. Then it's going to end when x is 7. Well, when x is 7, absolute value of 7 is 7. 7 minus 3 is 4. That's where I got that point, the ordered pair 7, 4. At that time, I needed to just connect all the points and graph out my function, making sure to note any areas above the x-axis that are going to have positive values, any areas beneath the x-axis that's going to contribute a negative area. So while I say, hey, the integral of this function, it's the summation of these areas, I need to keep in mind area 2 is negative. due to the fact that it's beneath the x-axis. Now, the way I account for the negative is I just give it a negative y value for the height, and that makes sure I account it as a negative. The first region, A1, the base goes from -5 to 3, so my area formula, 1/2 base times height, 1/2 times 2, the base, the height of 2. And then in the second one, 1/2 the base. Well, the base starts at -3 and ends at 3. That's a distance of 6 and a height of -3. And that ensures that I account that as a negative. And then my last one, it has a base from 3 to 7. So 1/2 times the base of 4 times the height of 4. And then when I go ahead and calculate that out, I'll have 4 divided by 2 is 2. My middle region will be 18 divided by 2 minus 9. Then my last one, 16 over 2 for plus 8. So the total net area of this region, our book would call it the net area, is a net area value of 1. In the next one here, we're asked to evaluate the following integral using the fundamental theorem of calculus. Okay, so this would be the evaluation theorem. And you'll notice when I created this for my notes, I'd forgot to put the ds beside this problem. If I happen to do that on the test, you could go ahead and integrate it with respect to s as I intended, or you could say problem cannot be solved because you did not tell me the variable of integration. So this wasn't there. I had to add that in as I was doing my solutions here. Hopefully I'll fix that for the actual test problem. But now, when I'm looking over this, I can say, well, it's the integral of this function with respect to s. This is the fundamental theorem of calculus, the definite integral evaluation theorem portion of it. And I can say, well, just like some of our earlier problems, you're going to have to simplify algebraically first before you can do anything. And I'll also try not to use s as a variable because my s's and my 5's look so similar. I apologize for that, guys. This first one, 5s squared divided by s cubed, that should simplify to be 5 over s there. That's a 5 in the numerator, s in the denominator. My second one, minus 4 over s cubed, that gives me minus 4s to the -3. At that point, I'll use the power rule on the second term. The first term is the exception to the power rule because s is to the -1 power. That's when we just say, well, it's the natural log. Usually we would have to say the absolute value of s. I did not have to here because all of our values of s are already guaranteed to be positive anyway. So I can say, okay, at 5 natural log of s plus, and when I integrated this second one with the power rule, it became minus 4s to the -2 divided by -2, which is where I get the plus 2s to the -2. And then I can say, okay, my definite integral says I need to evaluate this from 1 to 5. I went ahead and cleaned up my second term from here to here, and I just said, well, that's better written as 2 over s to the second. Now I evaluated. You always evaluate at the upper limit of integration and say, well, this is going to be 5 natural log of s evaluated at 5. So it became 5 natural log of 5 plus 2 over 5 squared becomes plus 2 over 25. From that, we're subtracting this function evaluated at 1. Well, we know the natural log of 1 is 0, so that's where that came from. And then I'd get 2 over 1 squared for 2. So then when I'm simplifying, I'll have that 5 natural log of 5 term plus 2 over 25 minus, I thought of that as minus 50 over 25. 2 over 25 minus 50 over 25 gave me a minus 48 over 25 for my final answer there. Moving on down. This is another part of that fundamental theorem of calculus where we can say, okay, we know a derivative and an integral are inverse operations. So what we're going to end up with is the inside function evaluated at the limits of integration here, as long as those limits of integrations are variable of the original derivative here. If they're not, we know that the derivative of any constant is just a 0. So we could say whatever this function integrates to be, if we evaluate it at 18, it's just a constant. And then the derivative of any constant is 0. That's where that first term comes from. But then for our second term, we can say, all right, we know that whatever the integral of this is, the derivative is going to undo it. So it's going to be the function on the inside here, which is understood to be 1 over t to the 7th plus 4, evaluated at your limit of integration. And please remember, we always subtract the lower limit. That's where that came from. So minus 1 over, not t to the 7th, but my limit of integration, tangent of z to the 7th minus 4. Now, this part comes from right here is because now whenever you plug that in and then take the derivative, you've got a function inside of a function. So we have to worry about the derivative chain rule. So we say, well, it's going to be minus the function evaluated at the limit of integration times the derivative with respect to z of the limit of integration. And then we know, well, the derivative with respect to z of the tangent of z is secant squared z. So I put that secant squared z up into the numerator here. It was already multiplying by a -1. I get negative secant squared z over that denominator of tangent to the 7th z minus 4. That is a fun problem. Moving on down through here. Number 10. We're supposed to approximate to 3 decimal places all points at which f of x is equal to pi over 4 sine x equals its average value on 0 to pi. Okay, average value of a function. F bar is equal to 1 over pi minus 0 on the integral from 0 to pi of pi over 4 sine of x dx. So it's just the integral of f of x dx. I plugged that in here. Now, that pi over 4 is just a constant, so it can get carried along with the integrable function sine of x. We know that the derivative of sine is cosine, so the integral of sine would give me negative cosine. I went ahead and wrote my answer as negative pi over 4 cosine of x. Now, out in front, we're multiplying by 1 over pi. I accounted for that by dividing my answer by pi. And then, of course, we have to evaluate at our limits of integration from 0 to pi. Now, when I did that, and actually in my simplifying here, what I went ahead and did is I said, we know that this pi and that pi are going to cancel out. I'll have a factor of -1 in my numerator and a factor of 4 in my denominator. That's where that came from. And then it's just evaluating the inside, cosine of pi minus the lower limit of the cosine of 0. Well, the cosine of pi is -1. Cosine of 0 is 1. So you got -1 minus 1. That's a -2 on the inside. But I had a -1 on the outside. -1 times -2 would give me a +2. I get 2 in the numerator, 4 in the denominator. 2 over 4 is 1/2. Now, that is the average value of the function. That's my f bar. The average value of this function is 1/2. What the mean value theorem stipulates is that f of x must attain its average value for some value of x between 0 and 2 pi, and it could be values plural. So in order to find the values of x where that average value occurs, you set your original function equal to your average value here. And then when I did that, I said, well, okay, in order to solve for the angle where this is going to occur, I need to get the sine by itself. I multiplied both sides by 4 over pi to get rid of that. When I did that, my 4 and my 2 canceled out. It left me a 2 in the numerator, pi in the denominator. So I need to know, when does the sine of x equal 2 over pi? That is not one of the values that we should be super comfortable with on the circle. However, what I did know is that my calculator is only going to give me one of the two answers. I've got to answer all values between 0 and 2 pi. Sorry, between 0 and pi, not 2 pi. So what I did on my calculator is I found out how high the 2 over pi was, and when I did that, 2 divided by pi ended up giving me like 0.637. So I went to my unit circle and I said, this is literally asking me, when is the sine of pi equal to approximately 0.637? So I drew a y value approximately 0.637, labeled it 2 over pi, and I said, yes, there's going to be an answer in quadrant 1. This is the answer that the calculator can give me. I needed to also know that there was a second answer over here, because I know that the y component on the unit circle is every bit as positive as it is over here in quadrant 1. Okay, now the solution that my calculator assisted me in was this one over here. Please remember to be in radian mode. When I went inverse sine of 2 over pi, I got 0.690 rounded to 3 decimal places. That's this angle x sub 1 here. That's how much you would have to rotate up to get to where the sine is this value 2 over pi. And then I can say, well, okay, but there's another angle in quadrant 2 that would still be between 0 and pi. And in order to get to that, I just said, well, it's the full rotation of pi minus this angle of 0.690 radians to get to x sub 2. That's where this answer comes from. In order to check those answers, I promise you, you could take the sine of this and the sine of that, and you would get your approximate value equal to 2 over pi. It's going to be the 0.636619 answer. Okay, up next, looking at number 11. This is where we get into my favorite of our sections, the substitution. So no really techniques of integration on this until we get to this. We had rules before. Now we're using the substitution technique. In this one, we know that we should always I shouldn't say always, usually let u equal what's inside of a group to a power. So I can say, well, if I let u equal x to the third plus 13, then the derivative of u is going to be 3x to the second with respect to x. Now, in the problem, this is supposed to have a 3x squared dx if this is a viable technique of integration. I don't see the factor of 3, but we can always multiply by a factor of 3 on the inside if we divide by it on the outside. That's why I showed this next step here. What I did is I rearranged the order of the multiplication. I said, let's call this the integral of x to the third plus 13 to the 23rd first. Then that factor of x squared can come out at the end, along with the factor of 3 that I'm forcing on the inside. So if I multiply by a 3 on the inside, I have to make up for that by dividing by 3 or multiplying by 1/3 on the outside. The reason we do this, though, is now that 3x squared dx, all of that's going to get replaced with a du. My x to the third plus 13 raised to the 23rd, all of that's going to get replaced with a u to the 23rd. The whole point of substitution is to take something that doesn't work with the basic rules. So this, if you tried to just use the power rule, doesn't work. But now it's taken that and it's made a function where now power rule works no problem. You just say, well, the integral of u to the 23rd with respect to u is u to the 24th divided by 24 plus your constant of integration. Then you can say, well, okay, I'm going to take that 1 over 3 times 1 over 24, call it a coefficient of 1 over 72 out in front, times u to the 24th plus the constant of integration. Then my last step, replace u with what it's worth, the x to the third plus 13th. And we get 1 over 72 times x to the third plus 13 raised to the 24 plus that glorious constant of integration. And we've done our first substitution problem on this test. The next substitution problem, more fun, more tricky. It's just that the variable x doesn't cancel out like it did in the last one. We had an x cubed. We needed an x squared on the outside. We had the x squared on the outside. The only thing we had to do was multiply by the factor of 3 that we didn't. This time, the group inside, or the innermost group, is that x plus 20. So I say, well, let's let u equal x plus 20. But the derivative of u is just the derivative of x with respect to x. You say, well, that's just 1 with respect to x. Yeah, du is dx. That tells me that the substitution can be done because I can just replace the dx with a du. But the problem is nothing got rid of this x in the substitution. So we use our equation for u and say, well, we know u is equal to x plus 20. Thus, x, if you subtract 20 on each side, we can see is equal to u minus 20. I had to use that to substitute for x in the numerator and get the u minus 20. My denominator just becomes the square root of u, and then dx becomes du. Now, you need to understand this is far better than the original format. In the original format, I could not solve algebraically, so I couldn't simplify. Over here, I can. This is nice because we can distribute that square root of u into each term in our numerator. U divided by the square root of u just gives me u to the 1/2. Minus 20 over the square root of u gives me minus 20 to the negative 1/2. We did this because now it's very easy to use our power rules. U to the 1/2 becomes u to the 3/2 times the reciprocal, 2/3. Minus 20u to the negative 1/2 becomes minus 20u to the positive 1/2 divided by 1/2. Negative 20 divided by 1/2 is where the negative 40 comes from there. And then we have our u to the 1/2 power plus the constant of integration. After that, the only thing I did was clean it up. I don't want the final answer in terms of u when the problem is given in terms of x. So, and I always put it back in radical form. If the original problem's in radical form, my answer will be in radical form. So this first one, I can say, well, this u to the 3/2, I need to understand that that is the square root of what u is equal to, x plus 20, raised to the 3rd power in the numerator. So I get 2 on the square root of x plus 20 raised to the 3rd in the numerator, all divided by 3 there. My second one is just minus 40 on the square root of u, which is minus 40 on the square root of x plus 20 plus our constant of integration. Problem 13. Usually students have a little bit more trouble with trig problems in the substitution. Please do remember, you will be expected to know all 6 of your original trig derivatives. That's very important in a problem like this. If I didn't keep in mind that the derivative of cotangent was negative cosecant squared, I wouldn't know how to do this problem. So when I see my cotangent and my cosecant squared in this problem, I can say, well, I know that I want to let u equal the cotangent. Then if I do that, the derivative of u is going to equal negative cosecant squared x dx. That's what I'm showing right here. Now, since I needed that negative on the inside, I went ahead and rewrote that as the cotangent of x times the negative cosecant squared x dx. Remember, order of multiplication doesn't matter. That factor of 3, not helpful, so I just moved it to the outside. That's where that came from. So I said, I'm going to call this 3 on the integral from negative pi over 2 to negative pi over 4 of the cotangent x times negative cosecant squared x dx. This ends up being really nice because all of that's going to become du. This is just going to become u. So that's where this becomes this in the next step. It's just the integral of u du, which is super easy to integrate. Before I get down there, though, I also had to think about your limits of integration. I can't leave those from negative pi over 2 to negative pi over 4 because these are limits with respect to x, not with respect to u. So I had to say, let's use our equation to change our limits of integration. If u is equal to the cotangent of x, then u evaluated at negative pi over 2 becomes the cotangent of negative pi over 2. And that's cosine over sine, straight down in the unit circle. Your cosine, your horizontal component, there is 0. So that's where we got the first one. U at negative pi over 4, that's the point that splits quadrant 4 down there. And you say, well, if I'm splitting quadrant 4, you know your sine, well, that disappeared quicker than I thought. Your sine and cosine have the same value, but your cosine is positive, your sine is negative. So you'd say, well, a positive over a negative of the exact same term is just going to give me a -1. So then I can say, all right, I know my limits of integration. I have to replace the pi over 2 with a 0. That's why that's my lower limit. I need to replace the negative pi over 4 with a -1. That's why that's your upper limit there. So then I can say, well, all right, I evaluate my integral. The integral of u to the first is u to the second over 2, evaluated from your lower limit of 0 to your upper limit of -1, and then we multiply all of this by 3. The upper limit, when you evaluate it at -1, -1 squared is 1 divided by 2. That's where that came from. We know when we plug a 0 into this, we're just going to get a 0, so lower limit of 0. Our evaluation of the integral on the inside is just 1/2. We remember to multiply that by 3. We'll get 3 times 1 over half, 3 over 2. For number 14, we have the integral of 12 over 9x squared plus 1. So important in this one is that I remembered that the derivative with respect to x of the inverse tangent function is equal to 1 over 1 plus x squared. You've got to keep this in mind to be able to do this problem. So I can say, well, all right, this is similar to that, except I have a 12 in the numerator. Well, I went ahead and factored that to the outside. That's where that came from. Then I have 1 over, not x squared plus 1. If it was 1 over x squared plus 1, I said, that's easy. That's just the inverse tangent of x. It's not that. So you can either use the formulas there if you want to commit to memory the formulas that help you do that in this section. You can. I would rather use the substitution to help and say, well, okay, 1 over 9x squared plus 1, I want that to be a variable squared plus 1. It can't be x squared plus 1 because it has a coefficient of 9. So I just say, well, let's substitute. I want that to be 1 over u squared plus 1 because then I can call it the inverse tangent of u. So I let u squared take the place of where there's a 9x squared. Then the u substitution that I'm making in this problem, take the square root of both sides. I'll get u is equal to 3x. And then when I take the derivative of u, I'll just get 3 dx. So du dx would be 3. So du is 3 dx. Now, that means in order to do this substitution where I have all of this, I need to see a 3dx in the problem. So that's why in the next step here, you'll see I put a 3dx in the numerator. This dx was already assumed to be in the numerator. I'm multiplying by 3 on the inside that wasn't there previously. I have to divide by 3 on the outside. And since then, I can see this substitution is going to be possible because I can get a 3dx on the inside that will become a du in the next step. So I have to change my limits of integration when I know that that is possible. This is just evaluating your function u. You say, well, u evaluated at negative square root of 3 over 3, that's just 3 times the negative square root of 3 over 3. That's why I get the negative root of 3. So this is just going to multiply each of your x values by 3 when you plug it into this function. When I plug the upper limit into that, multiplies it by 3, just gives me the square root of 3. It cancels out that denominator in both cases. So I can say, okay, my limits of integration end up getting multiplied by 3 to become my new limits of integration with respect to u. Then this problem becomes du over u squared plus 1. By definition, this is the inverse tangent of u whenever we integrate it. technically plus c. We don't need that plus c, though, because we have a definite integral. We don't want the constant of integration. So we can say, well, all right, this part integrates to be the inverse tangent. I have my 4 out in front, and then I evaluate this from the lower limit up to the upper limit. I finished that out down here, and I said, well, then this integral is going to equal 4 inverse tangent evaluated at the upper limit, the square root of 3, minus 4 inverse tangent evaluated at the lower limit, the negative square root of 3. I tried to show my thinking here on a unit circle. This is literally asking me, hey, when is your tangent function the root of 3? I remember tangent's the ratio of sine over cosine, so it's asking me, at what value on the unit circle am I supposed to know where the y component is larger than the x component? And in quadrant 1, where our inverse tangent's restricted from negative pi over 2 to pi over 2, that's the only answers we can get. We can say, well, in quadrant 1, at an angle of pi over 3, my cosine is 1/2, my sine is the square root of 3 over 2. So the tangent of pi over 3 would be the square root of 3 over 1, which is exactly what I have here. So I can say, all right, then the inverse tangent of the square root of 3 is pi over 3. And you'll notice I went ahead and just factored back out my factors of 4 over here. And I said, this is my upper limit, the inverse tangent of the square root of 3, and then inverse tangent of the negative root of 3, that is asking you, where is the tangent function, the negative root of 3, such that the inverse tangent is defined, and that's at negative pi over 3, because at that value, your cosine is 1/2, and your sine is the negative square root of 3 over 2, tangent's the negative root of 3. But now, please keep in mind, it's always upper limit minus lower limit. So those ended up getting added together. And you could say, well, that's going to give me 2 pi over 3 times 4 for my total of 8 pi over 3. The problem 15, second to last problem. Your last two problems are both squares of a cosine or a sine function. They're using the trig power reduction formulas, which you do need to know. The only difference in your two formulas, if you're reducing the power on the cosine, it's 1 plus the cosine of twice the angle divided by 2. If you're reducing the power on the sine, it's 1 minus the cosine of twice the angle over 2. That's the only difference. Please notice both formulas always put it into terms of cosine. So I can say, all right, cosine squared is 1 plus cosine of twice the angle over 2. So when I work this out, I can say, well, I'll put my 1/2 out in front. I said that just creates a factor of 1/2 that I bring out here. Then my numerator, 1 plus the cosine of 2x, goes to the inside of my integrand. That's super easy to integrate. I can just say I'll leave my 1/2 out front. The integral of 1 with respect to x is x. The integral of the cosine of 2x, I want you to remember, anytime the angle, the inside angle is linear, you can do the reverse chain rule and say, okay, the integral of cosine is going to take me back to sine, and I'll always keep the angle 2x. If this were calculus 1 and I was taking the derivative, you would multiply by the derivative of the inside. You'd say times 2. We're integrating, that's why you divide by 2. So that's where this 1/2 came from. At that point, we've integrated. It's just a matter of evaluating. And please don't forget your 1/2 from out front. And I'll say I have 1/2 this integrand evaluated from negative 3 pi to 2 pi. When I evaluate it at 2 pi, x is 2 pi, and then plus 1/2 the sine of 2 times 2 pi, sine of 4 pi. But then I know that the sine of 4 pi, that's just going to be 0. So that makes all this term 0 here. I'll just have my 2 pi. Minus the lower limit. Well, when I plug negative 3 pi in for x, I get that. Plus 1/2 times the sine of negative 6 pi. Sine of negative 6 pi, just like the sine of 4 pi, that's just a 0. It's taking you back to a coterminal angle with 0. Sine of 0 is 0. Sine of negative 6 pi is 0. So this ends up just being 1/2 times 2 pi minus a negative 3 pi. The inside part is 5 pi. We divide that by 2 to get to our final answer of 5 pi over 2. Last problem. We have the integrand from negative pi over 34 to pi over 34 of sine squared of 17 theta integrated with respect to theta. Now, of course, it doesn't matter what the variable of integration is here. I'll keep it in terms of theta, but put my formula over here in terms of x. Of course, it doesn't matter. This sine squared 17 theta is going to be equal to 1 minus the cosine of twice the angle, that's where the 34 theta came from there, divided by 2. Rather than dividing by 2 on the inside, I prefer to just factor a 1/2 out in front. Then from that step, we just integrate. I'll keep the 1/2 out in front, and then the integral of 1 with respect to theta is where that theta comes from. The integral of minus cosine of 34 theta, I can say, okay, if I integrate a negative cosine, it's going to take me back to a negative sine. So that's why I have the minus sine. And I would get minus sine of 34 theta. Instead of multiplying by the derivative of the inside, we divide by the derivative of the inside. That's where that minus 34 comes from. That's our integral chain rule, where you're dividing by the derivative of the inside. And I can say, okay, now at that point, we evaluated our limits of integration from negative pi over 34 to positive pi over 34. I'll keep my 1/2 on the outside. When I plug pi over 34 in for theta, that's where I get this. Then we're going to have minus 1 over 34 times the sine of 34 times pi over 34. That ends up just being the sine of pi. But the sine of pi, that's just going to be a 0 there. Minus, when we plug the negative pi over 34 in, my angle theta becomes negative pi over 34. I'll get minus 1 over 34 times the sine of negative pi. Again, because 34 and negative 34 end up canceling out, and I'll just get the negative pi in for theta. But the sine of negative pi is just a 0. So this ends up canceling out, this ends up canceling out, and I just end up with pi over 34 minus a negative pi over 34, which I'll get 2 pi over 34. When I multiply that by 1/2 out in front, it takes me back to pi over 34, which is the answer to this question. Fun stuff. Okay, hopefully you think that this test is a good representation of your homework through here and not too burdensome. I think it's pretty fun stuff. Let me know if you have any questions, and I will be thrilled to help you out.